Okay, so since we have a varied audience in terms of previous knowledge in wave energy, I will start by introducing wave energy in general. Then I will give an introduction on the geometry optimization process that I was mentioning, the motivation for this research, the goal, and the method itself. And then I will introduce or go through some of the studies and results that I obtained by applying this method to different cases. And then I will draw some conclusions and highlight some aspects that could be studied further in the future. So why wave energy? So there's a high energy potential available in ocean waves, and the usable wave energy resource has been estimated to be 52 gigawatts, 52 gigawatts in the UK, about 300 gigawatts in Europe, and almost 3,000 gigawatts globally. And to use this extensive resource, wave energy converters have been studied and developed for many years. And although the first wave energy converter or the first wave energy harnessing concept dates from 1799, research in this field did not gain momentum in Europe until 1973 when the oil prices peaked. And so different concepts have been developed, and just for context, I would like to talk about the levelized cost of energy of these concepts. So the levelized cost of energy is a measure used to compare different energy generating technologies, and it represents the costs of building and operating a power generating device over the energy that it can generate over its lifetime. So the levelized cost of energy of wave energy converters today is around, or is estimated to be around 150 to 525 euros per megawatt hour. But it is expected to decrease to 75 to 115 euros per megawatt hour after a deployment of 10 gigawatts. For context, the levelized cost of energy of offshore wind today is around 100 euros per megawatt hour. So as I mentioned, different wave energy converter concepts have been developed based on different principles. And so here you can see some examples of these different wave energy converter concepts. Just to give you a quick overview, so starting from the top left, this is kind of the most common type of wave energy converter, we could say, where we have a floating body that oscillates with the incoming waves and reacts against a submerged body. This also exists as a in the fully submerged form, so just right next to it would be a similar type of concept, but fully submerged. Then we could, right next to that one, we have a very similar concept again, where the power takeoff system is enclosed inside of the hull. And so in this case, we would have a pendulum that rotates with the oscillation of the hull and generates electricity. And the last one on this row would be, again, a similar, we could call it a similar type of concept, but that oscillates in a different direction. In the bottom row, in the bottom left, we can see that, in the top row, we have single body devices where only one body is oscillating. In the top row, we can see that we have a two-body device where the two bodies are connected by a hinge. And within this hinge, we would have the power takeoff system. And then there's a range of other devices that operate based on very different principles. But for example, on the very right, at the bottom right, you can see what is called an oscillating water column, where we have a two-directional turbine through which air flows as the waves compress and decompress the air. And these were some examples of concepts. And here we have some wave energy converter concepts that have actually been developed and tested. And devices have been developed internationally, from the Pelamis device in Scotland, the Wello device in Finland, or the Oscilla Power device in the USA. Most of these devices have been deployed at a prototype scale, but for example, the Wello device has been tested at full scale in Orkney. And some of you might be familiar or most familiar with the Pelamis device, since this was the first offshore wave energy converter to generate electricity into the grid, and it was developed in Scotland. So using a simplified wave energy converter model, I would like to explain introduce the main components and functionality of a wave energy converter. So we can see that a floating body will oscillate with the incoming waves, and this oscillatory motion will be converted into electricity by a power takeoff system. Finally, we have a mooring line that keeps the wave energy converter, or WEC, in place. In a simplified, so these are the main components of a wave energy converter. And in a simplified way, to extract more energy from the waves, the natural frequency of the floating body needs to match the frequency of the incoming waves, since if they match, the body oscillations will be larger. So the natural frequency of the floating body will depend on its shape, on the device shape. And at the same time, we will not have just one wave of one frequency, but multiple waves of multiple frequencies in a real sea. The floating body will be subject to high loads in high energetic seas, such as after a storm. And of course, it should also be easy to manufacture to reduce costs. So it is not trivial how to design the hull or the floating body of a wave energy converter. And so this brings us to the motivation for this work on wave energy converter design optimization. So on one hand, as you could see, there's a wide range of wave energy converter designs. And this points to the need of early stage design tools to explore more of the design space and avoid expensive design iterations later on once the device has been built. On the other hand, the structure has been identified to have the highest cost reduction potential. And for this reason, many geometry optimization studies have been performed in the past decade. However, there was a lack of consistent methodology in these studies. So if we bring these 2 points together, we can see that there is a need for wave energy converter geometry optimization tools to improve the early stage wave energy converter designs with the goal of achieving or reducing the cost of the structure. So the main research question that we are trying to answer basically is, what is the optimal wave energy converter shape that reduces the levelized cost of energy? And to answer this question, I broke this down into 2 further questions, which are what would be a suitable method that generates shapes that not only maximize power, but consider other factors with an effect on costs? So what are the suitable methodologies, or what's the suitable approach? And secondly, how does then the optimal WEC shape vary depending on the general design and deployment conditions? So there might not be one optimal WEC shape for that fits all situations, but there might be different optimal shapes for different situations. So to address these questions, I developed this wave energy converter geometry optimization process. And this started by re-implementing a method that had been developed by the late Dr. McCabe, because this method was able to generate very diverse shapes. So it had a geometry definition that was very adaptable, and so it was able to come up with a wide range of shapes as a result of the optimization. So I did this based on his papers, and so I had limited information to re-implement his method. So I had to go through multiple iterations to make sure that there were no numerical errors occurring in the evaluation of these shapes, and to make sure that all of these errors were avoided and taken care of. So I will just go through the method step by step to introduce each of the parts. First of all, the geometry definition. As I said, I used the geometry definition as implemented by the late Dr. McCabe. And with this geometry definition, as I said, we want to be very flexible in the type of shapes that we can get. And so this is based on vertices of a polyhedron with an XZ symmetry plane. And these vertices can move randomly in space within some constraints, but basically can change their position in space. And then these vertices are then approximated by a bicubic B-spline surface, which is a smooth surface that approximates the points without necessarily going through them. So what you can see here on the right picture would be half of the submerged hole of a wave energy converter approximated through this method, where the white dots are the vertices and interpolated vertices in between. And the smooth surface would be the actual surface of the wave energy converter. So once we have the geometry, I can obtain the hydrodynamic coefficients or characteristics which describe how the shape behaves in waves with the help of a boundary element method software called WAMID. And this is a commonly used software to calculate the hydrodynamic characteristics of different shapes. Then I need to define where I want to place the device. And so I need to describe the wave climate. And just for context, for those with maybe less experience in wave energy, a real sea or an irregular sea is represented through the superposition of harmonic waves with a different frequency and amplitude. A sea state is then described by a spectral distribution that describes how the amplitude is associated to a wave of a certain frequency. So different types of spectra and so of distributions exist depending on the sea conditions that need to be described. And the resource at a given location will be described by a certain occurrence probability of different sea states. And so we have different sea states with different occurrence probability, and they are described, each of them, through one of these probability distributions of the different types of shapes occurring, waves occurring. And the location that I used for this study was mainly a location of the Shetland Shelf, although I did consider other locations, but the results that we will see today are for this location of the Shetland Shelf. So once I have a geometry, I know how it behaves in waves, and I know where I want to place it, I can calculate how much power it can extract at this location. And so for this, I used a simplified wave energy converter model where the power takeoff system is considered to be optimal and is modeled as damping, a stiffness, and an inertia terms. And in the original implementation, or the original approach developed by the late Dr. McCabe, devices were oscillating only in surge, so in the direction indicated in the drawing. But in this case, when I re-implemented the method, I made it so that it would apply to devices oscillating in any of the 6 degrees of freedom and any combinations of those. So the results that we will be discussing today also include devices oscillating in heave and in pitch, which is a rotational motion around the y-axis. So we have a geometry, and we can calculate the power for each geometry at a given location. So then, in terms of the optimization process, this will then select the better performing geometries based, for example, on their power production, and generate new ones. The function used to select better performing geometries or individuals in an optimization process is called objective function. And so in this case, if we were to select the shapes based on their power, then the objective function would be power, to maximize the power. So in the original implementation from the late Dr. McCabe, he used genetic algorithms for this purpose. And so genetic algorithms are based on evolution theory and the survival of the fittest individuals in a population. And in the present case, the population, or the initial population, consists of a set of geometries. And the better performing geometries are then selected as parents that will recombine and generate children. These children will carry genetic information from each of the parents, and some of the genes will be mutated. And so with this mutation step, we're introducing new information that was not present in the parents' generation. And the best performing individuals from the parents' generation are then reinserted into this new population to make sure that the best genetic material is kept in the population. So this will be the new population that will then be evaluated again. And this is an iterative process that in this case, or as originally implemented, finishes after a set number of generations. So say 100 generations. So this is the starting overall method. But if we go back to the original research questions, to the questions I introduced just before, you remember the first one was, are these what's the most suitable method to perform this geometry optimization? So to answer this question, basically I went step through each of these steps and looked at what is the most suitable method for wave energy converter geometry optimization. And so first, I studied the geometry definition by applying the optimization using more simple geometry definitions. So the question here would be, is there an advantage in using the more complex geometry definition that allows to generate more diverse shapes, or could I get equally good results by using a hemisphere, a cylinder, or a barge, and optimizing the parameters that describe the hemisphere, cylinder, and a barge? And so I optimized, I went through optimization, I applied the optimization, for each of these geometry definitions. And the result was that up to 224% higher objective function values could be achieved with McCabe's shape definition, so this more complex shape definition. And so the answer, the results showed that yes, it is worth the trouble to use this more complex geometry definition for WEG geometry optimization. Then I studied the objective function. As I mentioned before, we want to generate shapes that reduce the levelized cost of energy and not only maximize power. So I used objective functions that considered not only annual energy production, but also submerged volume or submerged surface area as proxies for costs. And I used them in different forms. So you can see the 6 objective functions that I used in the screen. And there's 3 that are based on the submerged volume and 2 based on the submerged surface area. And what they mean basically is that we are penalizing through these objective functions, we're penalizing either the submerged volume, the larger the submerged volume, the worse the shape. So the more material you need to use, the more expensive, and therefore worse of a solution. And so what do these different weightings mean? So in one case in here, we can see for function 3, for example, objective function 3, that I'm using the cube root of the volume. And this would kind of be equivalent to defining a characteristic length of the device based on the volume. And by using volume to the power of the 2/3, that would be equivalent to using a submerged surface area that is calculated based on the volume. In the same way, the cube root of the submerged surface area basically represents a characteristic length of the device that is calculated based on the submerged surface area. So these are the 6 options that I looked into. And here you can see some examples of the types of shapes that resulted from the optimization when using these different objective functions. And if you look at the resulting shapes shown here, you can see that when optimizing using volume as a proxy for costs in the objective function, the resulting shapes have thinner cross sections and have quite sharp edges, and so large curvatures. However, when using submerged surface area as a proxy for costs, the resulting shapes have larger cross sections and smaller curvatures. And so this means that optimal shapes resulting from optimizations using submerged surface area based objective functions are going to be easier to manufacture, since most manufacturing processes will have some type of constraint in terms of the maximal curvature that they can achieve, or even the number of curvatures. And because of the larger cross section, it will also be, or also from if looking at this shape, it will be also better from a structural integrity perspective, since the loads can be distributed more homogeneously compared to when you have very sharp edges. But also due to this larger cross section, it means we can have internal reinforcement structures, which would probably not be possible or very difficult in the shapes optimized for considering submerged volume as a proxy for costs. So overall, this shows us that combining annual energy production and submerged surface area in the objective function is the most suitable approach in terms of the manufacturability and structural integrity characteristics that the resulting shapes will have, while considering costs in some way in the objective function. And then I also looked at the suitability of the optimization procedure, or the optimization algorithm, actually. So as I had mentioned before, McCabe had used a genetic algorithm. And so I looked at using a different algorithm called the particle swarm optimization algorithm. And so the particle swarm optimization algorithm is based on bird flocking and fish schooling, and is represented through particles which are assigned a given position and velocity. And the position and velocity are updated in every iteration of the optimization algorithm by taking into account 3 terms. First, the position of the global best in the population. Secondly, the best position that each particle had been at so far. And third, the inertia of the particle, so the direction it was already following. And so different weights can be given to each of these 3 terms, and some randomness is also introduced when defining these weights. So different implementations of both the genetic algorithm and the particle swarm optimization algorithm were studied, making up a total of 14 different implementations, where different parameters, such as for example, the number of individuals in the population were varied, or I varied also the weights used for each of these 3 terms in the velocity update, or the number of parents selected for reproduction. And so the results showed that there is a preferred algorithm, or a preferred implementation, if you will, for each combination of objective function and number of modes of motion used for power extraction. So I considered wave energy converters extracting energy in surge only or in surge, heave, and pitch at the same time. And I applied the 6 different objective functions. And for each case, I used the 14 implementations, and this is the result. So for each of these combinations, a given implementation demonstrated to have certain advantages versus the others, resulting in more optimal shapes at the end, or faster converging and better shapes at the end. So after I had looked at the most suitable methods for each of the main steps of the geometry optimization process, I then went on to try to expand the method a little bit farther to look at the other factors that have an effect on the levelized cost of energy, and also to apply it to different cases. So the first thing I wanted to show you was the consideration of manufacturability. So I tried to expand the method to consider manufacturability in different ways. One of these ways was by saying what would the shape look like if it was made out of rolled sheets of steel. And so this was because this is the common manufacturing method used for ship hull manufacturing, where you have an internal structure and then rolled sheets of steel are welded on top of the structure. And the characteristic that rolled sheets of steel have is that they have curvature in one direction, but no curvature in the other. And so for this reason, I changed the geometry definition so that each geometry would be made out of 3 of these types of surfaces. And so the geometries that you can see on the screen are optimized to maximize power only, and oscillating or extracting energy in surge only or in surge, heave, and pitch. And so what the results showed me was that they were consistent with the previously obtained shapes. The shapes overall were similar, and there was no significant impact on the performance of optimal shapes. So they didn't perform significantly worse because of having this shape definition out of rolled sheets of steel. And so what we can say is that this approach to generate optimal shapes that can be manufactured out of rolled sheets of steel does generate good results, and it's a suitable approach. Then I try to take into account manufacturability in more general terms. So not only to improve manufacturability for shapes made out of rolled sheets of steel, but in general. So and for this purpose, I looked at curvature. So in general, for improving manufacturability, we want smaller curvatures. And so I tried to first constrain the maximum value of curvature occurring in a given shape. But this was too limiting, and it was very difficult to generate enough feasible geometries that would fulfill this constraint, even trying different numbers for this maximum curvature constraint. And so in a second step, I tried to use curvature as an objective function. So instead of just optimizing to maximize power or power over volume, I optimized for maximizing power on one side and minimizing curvature on the other. And so this is a multi-objective optimization approach. And I was able to generate shapes that had smaller curvatures with this approach. And then I just wanted to show you the results I got for looking at how the mode of motion in which the device is extracting energy affects the optimal shape, the resulting optimal shape. And in this case, I considered oscillations in surge, heave, and pitch, and all possible combinations of those. But today, I just wanted to show you a set of results for you to see what's the range of possible geometries that can come out of such an optimization process. So as you can see, for each column represents a different mode of motion for power extraction. So we have surge, pitch, surge and heave, and surge, heave, and pitch. And in the first row, the shapes were, the geometries were optimized to maximize annual energy production. And in the second row, or the lower row, shapes were optimized to maximize the annual energy production over the submerged volume. And so, as I said, this was just to show the range of shapes that can be generated. But if you have any particular questions on this, we can come back to this later. And so, in summary, there is a large wave energy resource that can be exploited with the help of wave energy converters. Wave energy converter design is not straightforward and needs to consider a number of factors. Design optimization is a useful tool to generate improved and novel designs without having to go through expensive build and test iterations. And a method for wave energy converter geometry optimization has been developed to support this early stage design. How can this be used? Why is the world a better place for having developed this optimization process? So this can be used by technology developers that can apply the method to generate improved initial designs for their wave energy converters and avoid more expensive design iterations later on. And I have been working with a wave energy developer, and we have achieved a 40% improvement in annual energy production versus their original design by applying this method. Obviously, this needs to still be validated with more detailed models and maybe some experimental tests, but this is still a very promising result. And then this can also be used by funding bodies who can use the work and comparison of the different metrics used for device comparison to be aware or to use these metrics for comparing different devices. And then the method developed here also can be used to find potential limits of devices in terms of the optimal relationships between power, volume, and surface area. And I am currently working in a project with, together with Wave Energy Scotland to develop this type of optimal relationships. So what's left for the future? There's plenty of things we could do, but I just wanted to highlight some of the main areas of research that would follow up from this, this research. So first, as I said, I developed an optimization approach to optimize the geometry of wave energy converters. However, the power takeoff system has a large impact on the system dynamics. And so the next step, and I had only considered an optimal power takeoff system. So the next step would be to optimize both of these components simultaneously so that geometry and power takeoff system parameters are optimized at the same time. Then the method could be extended to be applicable to other types of wave energy converters. So this methodology was developed for, is device agnostic, but it is basically only applicable for single floating body devices or two body devices. But as you have seen, there's a wide range of wave energy converters concepts. So yeah, the method could be extended to be applicable to more types of wave energy converter. As I said, I was trying to generate shapes that minimize or reduce the levelized cost of energy. And so to have a more holistic approach to this concept, I think it would be interesting to include reliability considerations. The same way I try to include manufacturability considerations, it would be interesting to include considerations in terms of the structural integrity for the different shapes. And finally, it would also be interesting to study the sensitivity to the model assumptions. So for this purpose, I used a certain model, which is based on a range of assumptions. So it would be interesting to see how by applying different models, the optimal shapes might vary or not, and so to find what is the most suitable model for this purpose. And so that was me. The research that I performed for my PhD was funded by the University of Edinburgh, Energy Technology Partnership, and Supergen Marine. If you want to stay in touch or you have any questions that we cannot solve today, please feel free to contact me in any of the ways you can find on the screen. And finally, as I said, now I'm a research associate at the University of Edinburgh in the Policy and Innovation Group. So if you are interested to know more about what we do, please feel free to have a look at our website. Thank you very much for your attention, and I'll be happy to discuss any questions you might have. Also, we have a final poll, actually. I don't know if we want to do that before the questions. Okay. Yeah, so my final questions for you were, do you think wave energy has the potential to become part of the energy mix? Yes, only for specific niche markets, or no?
We'll give everyone just a couple more seconds to select that answer.
Okay, well, it's nice to see that only one person in the audience seems to think that wave energy doesn't have the potential to become part of the energy mix, and most answers said yes. It's an ongoing discussion, I guess, if this is the case. Also, if in the development of wave energy converters, we should aim at being competitive in the energy market, or if we should be aiming for niche markets first. So yeah, there's no correct or wrong answer here. I guess the future will tell us. But thanks for your answers.
We have that final question.
Yes, and then we have a final question, which is, yeah, what do you feel is the biggest challenge for wave energy?
Few more seconds for everyone to get their vote in. Voting is anonymous, by the way, so just pick one, whichever one you feel is the most appropriate.
Great, thank you. So it seems like most people think that the biggest challenge for wave energy is the economic feasibility, and also quite a few people did choose the harsh sea conditions, so reliability and survivability challenges, which I think kind of fit into then the economic feasibility. So, and few people seem to think that environmental impact or social acceptance are the biggest barriers. So yeah, I guess if we understand that the harsh sea conditions actually have an effect on how much then it will cost to build the structure, then the biggest challenge overall is still the economic feasibility. Yeah, but hopefully by applying optimization algorithms like this one, we can improve our designs without having to invest large amounts of money to test so many devices. But yeah, thank you very much. That's very insightful.
Thank you, Anna, for your webinar today, and we have received loads of questions from our audience, so I hope you're ready for this. It's now our turn to go through the questions that have come from the audience. So for anyone who hasn't submitted a question, please please type it in at the bottom of your screen in the Q&A box, not the chat. Makes our lives a lot easier if we can see them all in one place. Alternatively, if you're watching on YouTube, please just type it in the box that is at the bottom of the screen. Please remember that this entire session is being recorded, so if you have to leave before we get to answer your question, it will be answered, and it will be up on YouTube at the end of the day with the video. So that's okay. We are scheduled to end at 2 o'clock, so we'll work through as many as we can till 2 o'clock, and then Anna and I will meet up later today to work through the remaining questions, because I can see that there's quite a few in the box already, but we'll give it a go right away. So Anna, you ready?
Yes.
Awesome. So the first question is from Simon, asking, actually refers to, I think, your abstract that was circulated. In the email invitation, the lead of this talk suggested that there was 52 gigawatts estimated to be the usable wave energy resource in the UK. Where does this estimation come from? Simon previously thought it was about 20 gigawatts combined wave and tidal.
Yeah, I guess there's different studies making this calculation. So I took this number from a study. I don't recall the study right now, but I would be happy to forward you that reference. I think that what might change in these different studies is, as you say, usable with energy resource. So I guess there's different ways of defining this. You can talk about the usable with energy resource. There's the there's the practically usable, technically usable, the overall available, without taking into account like the, I don't know, the ship routes and stuff like that. So I don't recall right now the reference, but I could forward that to you if you're interested. And it might be, the difference might come from how you defined the available wave energy resource. Mm-hmm. Yeah, okay. So it might be.
Right, thank you. Second question from Vahid, asking, when you optimize the shape, the wave structure interaction would change too. Do you run optimization over the whole process or just the different local objective function?
Well, thanks, Vahid, for the question. I need to reread that. When you optimize the shape of the wave structure interaction, do you run optimization over the whole process? I think that I understand that the question is asking, I do reevaluate the hydrodynamic coefficients, if that's what the question is about. So for each shape, I go through the whole process. So I evaluate the hydrodynamic coefficients for the new shape, and then I calculate the power based on these new hydrodynamic coefficients for the new shape. I hope this is what the question was about. Mm-hmm. If not, please write a follow-up question.
Yes, after. Please do. And obviously contact details for Anna are on the screen as well. Our next question is from Phil, asking, does this optimization of float design apply omnidirectionally, or does it demand a single wave direction?
Yeah, that's a good question. So the shapes that I showed were optimized with assuming a single wave direction, but the method can be applied for multi-directional seas. So for example, in the work I have done with the wave energy developer, we use this method taking into account multi-directional seas. So the results I generated and showed here are single wave direction, but it can be used for multi-directional seas as well.
Mm-hmm. Yeah. Next question asks, how did you change the vertices values every iteration? Does the optimization function give you those values like curvature and size, etc., for the next set of iterations? Does the shape update automatically within the code?
Thank you for that question. I'm sorry, I need to read that one more time.
So it is almost like three questions in one. So the first question asks, how did you change the vertices values every iteration?
Yeah, so each vertex is defined by three coordinates. The coordinates are defined as spherical coordinates. So there's a total of 11 vertices, and there's 22 coordinates that can be varied. The other ones are fixed because, for example, for vertices on the free surface, then the Z value is always 0. Yeah, so the 22 coordinates of these 11 vertices that are variable are my optimization variables. So those are varied in every iteration, or every geometry is defined through a set of 22 coordinates. Then the following question was, does the optimization functions give you those values like curvature and size for the next set of iterations? So depending on what the objective function is, if I am optimizing for submerged surface area, for example, then I will calculate the submerged surface area as part of my objective function calculation. If I am optimizing to reduce curvature, then I will calculate curvature as part of my objective function calculation. But I only calculate it if it is required, say, because otherwise I would just increase the computational time for no particular reason. But yeah, so it's calculated in every iteration for every shape when I do use those numbers in the optimization. And then the last question in there was, does the shape update automatically within the code? The answer is yes, that's kind of part of the optimization process. So new geometries are generated with the optimization algorithm. So as when I explained the genetic algorithm, when you generate the children, you're using characteristics from the shapes that you had already, and you're combining them to create new shapes, and you're introducing also some variations that were not present in your initial set of solutions. So you're then generating a new set of geometries automatically through the optimization algorithm that you then that I will then reevaluate. Yeah, I think.
The next question is from Simona asking, did you use any other methods to model the incoming sea wave other than harmonic sum? Can you please expand on the wave modeling?
Okay, thank you very much, Simona, for your question. The only way in which I modeled the incoming sea waves was through this superposition of harmonic waves. So I didn't consider any other way of modeling the waves, but also the hydrodynamic model that I use is the basic assumption is, well, the linear wave theory applies, so that we have small waves, and so oscillations are small, and that in this case we don't consider things like wave breaking or things like that would occur or we don't consider steep waves either. The reason for this is that in an optimization process, you have to perform the evaluation of each geometry. And so if you have a genetic algorithm with, say, 30 geometries for every iteration, and you run it for 100 generations, you have to perform this evaluation 100 times 30 times. So you need your evaluation to be fast. And so it's a very common approach to simulate the incoming waves as a sum of harmonic waves, where the assumption is then that basically that you can linearize your model because you have small oscillations. So the hydrodynamic model that I use is based on that assumption, and even if I were to use a more complicated model, it would still be based on that assumption. If you wanted to take into account a kind of wave breaking or things like that, then you would need to do probably something like CFD modeling, which would be too computationally expensive for an optimization process. But I don't know if Simona had something particular in mind, a certain type of wave representation that she knows about or that she was thinking about. So if you have a follow-up question, please write it down and I'll try to address that.
The next question is from Javier asking, what do you think about the simplification of saying that the power contained in waves can be measured in power per meter?
Okay, so I guess we're talking about the power contained in waves. Yeah, I guess it's a broadly used assumption in this field also to understand how much you're absorbing versus what is available, and then you use this capture width ratio. I don't have a particular opinion on the use of using this power per meter measure for the power contained in waves. I do have an opinion on using capture width ratio, which is the power that you absorb over the power contained in waves and divided by a characteristic width of device. I do not think that that is, if you are using it based on instantaneous power for say one wave period for the kind of the energy period and characteristic and significant wave height, for optimization of geometry, I think is not good, because then you're just going to generate a geometry that has its natural frequency matching this energy period that you're taking into account. And that is not, I don't think that is a realistic solution, because you will just have an extremely well-tuned device, but that might not perform well at all in any other situation. And secondly, defining this characteristic length, I think is very, you're kind of introducing additional uncertainty, because the characteristic length of a device or width of a device will depend on the type of the device, on the shape that you're using for that device. And so it makes the results for different types of devices less comparable, in my opinion. And so I would think I would not recommend using that measure for wave energy converter geometry optimization.
Mm-hmm. Thank you, Anna. I am aware of the time, and obviously we weren't scheduled to end at 2 o'clock. So we're going to try and answer the next question. And for everyone else who has submitted a question, but we haven't got the time to fit it all in this session, Anna and I are going to meet up later today, and we're going to record the questions and answers to those remaining questions, and it will be added onto the YouTube video that will be up by the end of today. So don't worry, all your questions are going to be answered. We just don't have enough time to work through them all. So I'm just going to finish off with the next question in our list, and then Anna, we will work through those remaining questions soon this afternoon. So that final question at the moment was, have you considered the natural period or making sure that every shape optimized is in resonance with the dominant wave period?
Well, I guess I kind of touched on this in the previous question. So I don't think that is what you want to achieve when you're optimizing the geometry for a wave energy converter. I think you want it to extract as much energy as possible over a range of C states, so that it not only performs really well in one C state, even if it's the predominant one, but that it is capable of absorbing energy at over a quite wide bandwidth. So I would say that that is not what you would aim for when you're doing geometry optimization of wave energy converters.
Okay, so our next question is asking, there seem to be some approximate dimensional assumptions in your analysis, roughly 10 meters by 10 meters. Can you say something about why this size is chosen? Is it dependent on the local wave climate?
Yeah, that's a very good question. So there are limits on the total allowed volume and the maximum value for the radius. So for each coordinate, for each vertex, sorry. So so that when maximizing power, the algorithm does not just converge into infinitely large shapes. So these values were just directly adopted from McCabe's approach. But when applying this method, for example, to another wave energy converter device, I changed these limits to fulfill the volume constraints by the developer and to be able to generate enough feasible shapes. So this is a good example of the assumptions that could be studied further in the future.
So the next question is asking from VVS, asking, for each shape, the drag coefficient is changing drastically. Does your optimization technique consider this?
Yeah, that's also a very good point. Thanks for the question. So I use a frequency domain model to calculate power. So drag is not considered. If a time domain model was used, then viscosity effects could be considered. However, drag coefficients can only, or I understand that you would require CFD modeling to obtain the drag coefficients, which would be too computationally expensive within an optimization process to calculate for each shape. So you would require some type of approximation for the drag coefficients in that case to be able to take that into account. But yeah, my current, the way that the optimization is set up and the model I'm using does not take that into account.
Next question is asking, what is the main step from the work of Andy McCabe?
Okay, so the method was extended to work in various degrees of freedom rather than just one. And it was also extended to avoid numerical errors that would interfere with the selection of optimal shapes. Then apart from these extensions, each of the elements used within that original approach were further studied. And in some cases, other approaches, such as for the definition of the objective function or for the choice of the optimization algorithm, were found more suitable than they used in the original study. So in that sense, more suitable methods were found for this approach. And then finally, I added further considerations to the optimization process, such as the manufacturability considerations I talked about today, but also mass distribution considerations. And I then applied also this further developed method to understand the effects of modes of motion for power extraction on optimal device shape, and also to understand the effect of location. So it's an extension of the method and an application of this extended method to further cases, I guess.
From Alistair, he asks, have you looked at how well your volume or area proxy for costs relates to the actual cost? For example, that may cover material, but what about manufacturing process?
Yeah, again, that's a very good question. Thank you very much. So proxies for costs are used because it is very difficult to calculate, for example, the levelized cost of energy at these initial development stages. And even considering specific costs of materials or manufacturing processes is very difficult because they depend on a lot of factors. So I looked into defining manufacturing costs based on manufacturing complexity represented as manufacturing time. However, you need to know exactly what manufacturing processes you would require to build each shape. And so it's not straightforward to include this in an optimization process where you have very different geometries that can result from the optimization, and where then you would need to select what's the most suitable material and manufacturing process based on the shape. So I think this is a very interesting topic of research, but yeah, it's not straightforward to go from these cost proxies to actual costs. Yeah.
Next question is from Said asking, I understand that submerged WECs have a lower LCEO. Wouldn't it be better to focus research on these? If you could just clarify what LCEO means, that would be really helpful.
Yeah, I think this, maybe there's a small typo and this means LCOE. So this would be the levelized cost of energy. So meaning that the submerged wave energy, I think this person is suggesting that submerged wave energy converters have a lower levelized cost of energy, so a lower cost to generate electricity. I think it is very difficult to quantify the levelized cost of energy at early stages of development. And so, as I just said, so quantification of these values are really dependent on the underlying assumptions. And so in my understanding, there is not a clear preference for a given concept, since they all have different advantages and disadvantages. And these advantages and disadvantages are really difficult to quantify in terms of a final economical benefit. So yeah, although submerged wave energy converters for sure are a valid solution with a clear potential, in my understanding, there's no preferred concept, and it is very difficult to really say that at this stage. Yeah.
Next question is asking, most of the body's surfaces you showed appear to be the main floating part of a point absorber. Could your work be used to evaluate multi-body attenuator devices?
Yeah, thank you very much for that question. Yes, the short answer is yes. The longer answer is the optimization process is applicable to any device. The main difference in this case would be that the hydrodynamic model that you would use for calculating the power would need to be specific for this attenuator device. But in my previous work with a technology developer applying this method to improve their device design, for example, we used their power calculation for their specific device in combination with my optimization process. So you can imagine this optimization process to be set up modularly, where any of the elements that I showed in the flowchart can be adapted or replaced depending on the requirements. So I believe that yes, it could be used for a multi-body attenuator device if we would adapt the hydrodynamic model.
And we are finally on to our last question, asking, you are now optimizing the hydrodynamics of WECs. You put PTO, WEC type, and structure aspects as your future work. How many challenges will you have to consider all these aspects simultaneously? Is it achievable?
Yeah, thank you very much. Yeah, so considering other wave energy converter types is a matter, as I was mentioning before, of having a different hydrodynamic model for each type of device. So if you would have a set of hydrodynamic models capable of representing the dynamics of different types of devices, you could basically almost use the optimization process one-to-one for these different devices. I wouldn't consider different wave energy converter types within one optimization process. You would need to run it every time for a different concept. I don't think you want to be choosing the concept within this optimization process. And so this would be relatively straightforward, I think, to consider other WEC types. In terms of the reliability, I did develop a simplified method for accounting for reliability together with Dr. Clark, who is currently a researcher at NREL, using damage equivalent loads. And so this method, for example, can be used in the optimization process without increasing computational time significantly. But it still needs to be validated with more detailed models, such as using FEM analysis to ensure that the damage equivalent loads calculated based on this on the expected PTO force, which I calculated based using a frequency domain model, is representative for the reliability characteristics of the device, and that the resulting optimal shapes do really have better reliability characteristics. So we would still need to validate the results by performing a more detailed study of the method and of the resulting shapes to see if they truly improve reliability characteristics. But I think it is achievable. You just need to find the right simplified method to do this. Yeah, I think that's my answer.
Great, and thank you so much, Anna, for working through these questions that we got from your MASTS webinar earlier. You were a great presenter, and we had a great series of questions that come through. And thank you very much.
Thank you very much for letting me. Yeah, and thank you everyone for the questions and for joining today.
For everyone who is still with us, I know Anna has to quickly move off into another meeting, unfortunately, but I would just like to highlight the upcoming other webinars that we have coming onto the MASTS webinar series. We are ending on the 2nd of September. That's because we're giving ourselves a bit of a break before the MASTS annual science meeting. The deadline for speakers is the 14th of August. So if you were considering submitting an abstract, you have a few days left before that. We are also opening soon our e-poster abstracts as well. So keep an eye on the MASTS website if you're interested in participating in the online annual science meeting that is happening in October later this year. If any of these webinars that are on your screen interest you, please check out the registration page. That is what you used to join this very webinar today. And you'll be able to join just like you have today. So every session is always recorded. So if you aren't able to join, but you do like the look of some of these other talks, please check out our MASTS YouTube page after those dates. Thank you for joining us today for today's MASTS webinar. We hope you can join us again soon.